Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on random signal theory. We are still in chapter 3, discrete random variables, and we have been talking about special distributions. So after finishing the basic information that we need, which is basically the probability mass function, the cumulative distribution function, the mean, and the variance that we can calculate for any discrete random variables, we devoted some lectures to talking about some special distributions, special discrete random variables. So in the previous videos, we talked about the discrete uniform distribution. We talked about the binomial distribution. And in this video, we will be talking about a close relative to the binomial distribution, which is called the geometric distribution. Let's try to recall the binomial distribution, and then we take it from there. So what was a binomial random variable? A binomial random variable looks like this. We repeat a Bernoulli trial. We have a Bernoulli trial, which is an experiment with only two possible outcomes, success or failure. We repeat it n times. So we repeat that Bernoulli trial a predefined number of times, which is given, and then we observe the number of successes. So a very simple example, I give you a coin, and then I ask you, please toss this coin 10 times, and then tell me how many heads did you obtain out of the 10. So if we let variable x denote the number of heads that you obtain after the 10 experiments, this variable x is called a binomial variable. Now, what about the geometric random variable? Again, it's a close relative to the binomial random variable because it also depends on a repetition of Bernoulli trials. Let me start with the same example before we talk about the general statement. Let me mention an example first, the tossing a coin example. I give you a coin and then I tell you toss the coin. I don't define how many times you need to toss it, but I tell you toss the coin and keep tossing the coin until you get a head, until you get the first head, and then you stop. What you need to observe is how many times you had to toss until that success. That's a very important distribution, a very important random variable. Imagine also it would appear if you call maybe a call center. So there is a busy call center like a TV station or whatever kind of call center, and you need to make an important phone call. So sometimes you get a busy tone. So you try, it's busy. You try again, it's busy. You keep trying until the call goes through, until you are successful. And then obviously you don't have to repeat, right? So an obvious phenomena to observe here in this case is how many times did you have to try? Did you have to call only once and then it was successful right away? Or did you have to call twice or 3 times and so on? So this is the geometric distribution. So what is a geometric distribution? Let me use my own slide here, my own illustration. So a geometric random variable can be defined as follows. A Bernoulli trial with probability of success equal to p is definitely a parameter. So the individual Bernoulli trial has success probability p, and that Bernoulli trial is repeated until the first success. So we repeat until the first success. That's the obvious difference between geometric and binomial. In binomial, we have a number of times that we repeat and we observe the number of successes. But in geometric, we keep repeating. We don't know how many times we repeat. We keep repeating until the first success, and then our variable x denotes the number of times we needed to repeat until that first success, so the number of trials needed until that first success. Let's look at this example that we will use to basically establish the probability mass function for a geometric distribution. You toss a coin until a head is obtained. Do you notice the difference? It's not you toss a coin 10 times and then observe the number of heads. No, you toss a coin until you get a head, and then let x equal to the number of tosses needed until the first head. Find the probability that x equal to 3. In words, what is the probability that you had to toss 3 times until you obtained the head? How can we construct this probability? It's very intuitive. What is the situation in which you have to toss 3 times? You are tossing until the first head. So when do you really need to toss 3 times? If the first one was a tail, and the second one was a tail, and then the third one is a head, there is no other possibility. Because once you get the head, once you get the success, you stop, right? So what is the probability that you had to repeat 3 times? It is the probability that the first 2 times here, 3 minus 1 is equal to 2, that the first 2 times are failures. So if P is the probability of success, 1 minus P is the probability of failure. It's the probability of getting a tail. So 1 minus P to the power of 2 times P. There is no choose and choose X. It's not available because we don't have any different combinations possible. We don't have any different possibilities. The only possibility here to get basically to need to toss 3 times is that the first 2 times are tails and then the third one is a head. So the probability that X is equal to 3 is simply 1 minus P to the power of 2 times P, or P times 1 minus P to the power of 2. More generally speaking, what is the probability that our variable X, do you still remember the meaning of this variable X? X denotes the number of trials needed until the first success. In this example's context, X is the number of times we had to toss until the first head is obtained, and then we stopped after that. So the probability that this variable X is equal to any value, X is equal to P, which is the probability of success. We have only one success, remember. The success comes at the end, times 1 minus P, which is the probability of failure, to the power of X minus 1. X is this number given here, to the power of X minus 1. Because always in a geometric distribution, we have X minus 1 failures, followed by 1 success. So the probability mass function for a geometric distribution, f of x, little f of x, is equal to 1 minus P to the power of X minus 1 times the probability times P. What are the different values of X? Again, what was the meaning of X? Was it the number of successes? That's in binomial. But X in the geometric distribution denotes the number of times you had to repeat the experiment. So definitely we repeat it once at least. If I give you the coin, please toss until the first head is obtained. So definitely you will toss at least once. So X is 1 or 2 or 3 and so on, and it can possibly go until infinity. So these are the different values for X. What you see here is the probability mass function of the geometric distribution, and using this function we can simply substitute to obtain probabilities, like what is the probability that we had to toss 5 times until the head is obtained. Mathematically, it is the probability that X equals to 5, and we just substitute P times 1 minus P to the power of 4. P times 1 minus P to the power of 4. What else can be obtained for a geometric distribution? If X is a geometric random variable, it can be shown that the expected value of X is equal to 1 over P. 1 over P. P was the success probability of the individual experiment. Let's, as a simple example, focus on the tossing a coin example. Here, you toss a coin until a head is obtained. It's a fair coin. It's a fair coin. So what is the probability of getting a head? If you toss it once, what is the probability of getting a head in that trial, in that experiment? 0.5, because it's a fair coin. So what is the average number of tosses? This is the expected value, or mu. The average number of tosses that you need until a head is obtained, it's 1 over 0.5, which is 2. Again, looks intuitive, looks natural, it makes sense. It can also be shown that the variance of X is again a geometric random variable. The variance of X, or sigma square, is given as 1 minus P over P squared. Maybe the best thing that we do here is to see an example that uses the geometric distribution, and we see what we do here. In a communication system, the probability that a message arrives with no error is 0.8. So if I send this communication message, there is a probability 0.8 that it arrives correctly with no error. Obviously, the probability that this message arrives with error is 0.2, and since this is the only case I'm talking about, it means that sending the communication message is a Bernoulli trial, because if you send this message, either it arrives with no error or it arrives with an error. We don't have any other cases mentioned here. The message will be retransmitted until it arrives successfully. Imagine that we have a reliable communication system. If I want to send you a message, that message must arrive successfully. So if it arrives with the error, I have to send it again. If it again arrives with an error, I have to send it again, and I have to keep doing that until that message arrives successfully. Now, let's look at these two questions here that are related. What is the probability that we need to transmit the message 3 times in total until it is successfully delivered? What is the probability that we have to transmit this message 3 times in total until it is successfully delivered? Obviously, when do we have to send 3 times? If the first one is a failure, it arrives with error, and then I try the second one again with error, and then I try a third one, but this one is a success. So it's a geometric distribution. It's a geometric because I'm asking about the probability. I'm asking about the probability that we have to transmit 3 times in total until the first successful delivery. So what we observe here is the number of times we had to repeat until success, and how. So basically this means that we have a geometric random variable. Let's basically mention a comment here. In the case of the binomial distribution and the case of the geometric distribution, we don't have to tell you that it's binomial or geometric. This is recognized in the context. This is recognized from the context of the question. So here we're sending a communication message, no error with probability 0.8, obviously with the error with probability 0.2. So we have a Bernoulli trial. We have only 2 options, success or failure. And then we notice that we're repeating this until the first success, until successful delivery, and the question is about the total number of times. What is the probability that we have to send 3 times in total until successful delivery? So this is a geometric question and not a binomial question. So to solve it, we have to substitute in the geometric formula, the geometric equation, which is p times 1 minus p squared. That 2 here in the exponent is just simply 3 minus 1, right? What was p? 0.8. What is 1 minus p? 0.2. So in short, 0.8 times 0.2 to the power of 2. Calculating this, it is 0.032. So according to these numbers, the probability that we have to repeat the message exactly 3 times until it is successfully delivered is 0.032. A follow-up question B here, what is the average number of transmissions needed? On average, how many times do we have to transmit this message until it arrives successfully? Since we have a geometric random variable, average means expectation, expected value of x, which is 1 over p. Remember, we are not using n times p. This was the expected value for a binomial distribution, but here we have a geometric distribution, so the expected value is simply 1 over p, and p was 0.8, so 1 over 0.8, which is 1.25. So on average, we have to retransmit, we have to transmit the message in total 1.25 times until it is delivered successfully. So this concludes the geometric distribution, and as you have noticed, it's a close relative to the binomial distribution. In both cases, we are repeating a Bernoulli trial. However, in the binomial case, we are repeating the Bernoulli trial a number of times, which is given like n times. I tell you, toss 10 times or 12 times and so on, and then what we observe is the number of successes among the total. However, in the geometric distribution, we don't have a predefined number of times, but we say that we will keep repeating until the first success occurs. So this is the geometric distribution, and this is a representative example on the geometric distribution. We have only one distribution left, which is the Poisson distribution, and that's why we will finish it in this video. So what is a Poisson distribution or a Poisson random variable? Let me start by saying that the Poisson random variable or the Poisson distribution is used in the context or the setting in which we have random events occurring during an interval. Let's say, for example, we are waiting at the bus stop for 1 hour, so we have a time interval of 1 hour, and buses arrive at random during this hour. In this case, we can use the Poisson random variable to basically model how many buses arrive during this hour, the number of occurrences of this event during our time interval. The interval does not have to be time. It could be an interval in space, like if we're reading one page of our book and we notice that in this page, we notice that typos or errors occur at random in this page. So if we need to basically model the number of errors or typos that occur in the interval of one page. Again, we use the Poisson distribution to model this. So bottom line, what is a Poisson distribution? The Poisson distribution, or the Poisson random variable, is used to model the number of occurrences. How many occurrences do we have of this event during an interval? What is the parameter of the Poisson distribution? It's called lambda, the Greek letter lambda, which indicates the average number of occurrences during the interval. This is known. So if I'm waiting at the bus stop and I'm observing buses that arrive at random, what I know beforehand is the average number of buses per hour, let's say. So if we say we have 5 buses on average per hour, this is something that we know in advance. However, what we don't know is the actual number of buses that arrive during the hour that we're standing at this bus stop. So this is not known. The actual number of buses is something random. However, the average number of buses that we call lambda, or in general, the average number of occurrences of our random event during the interval, is called lambda, and this is known. That's why it's a parameter of the Poisson distribution. Now, what is a Poisson distribution? If we have random variable x, x indicates the number of occurrences of our event during a time interval. We say x, random variable x, has a Poisson distribution, or x is a Poisson random variable if its probability function f of x, if its probability mass function f of x is given by this equation, by this formula. Lambda to the power of x, e to the power of minus lambda, divided by x factorial. Again, lambda was the parameter which indicates the average number of occurrences of our event. But this equation, when we substitute with different values for x, we can calculate the different probabilities that we have a certain number of occurrences of our event. Like if we say, what is the probability that variable x equal to 3? First of all, what does this mean? It means the probability that we have 3 occurrences of our event during our interval. The probability that x is equal to 3 would be given by lambda to the power of 3, e to the power of minus lambda over 3 factorial. So we substitute with different values of x according to which probability we want to calculate, but lambda is our parameter, which is the average number of occurrences of this event during our interval. Now, before we proceed, what are the different values for variable x? Again, what did variable x indicate? Variable x indicates the number of occurrences of this event during an interval. So how many buses arrive during an hour, or how many typos happen in a page of a book, or how many packets arrive in a computer network, and so on. So this could be 0. Obviously, the number of occurrences of this event could be 0. So if no bus arrives during our time interval, x is equal to 0. If 1 bus arrives, x is equal to 1. If 2 buses arrive, x is equal to 2, and it could go until infinity in the Poisson distribution. Let's give you an example. Before we proceed, let's give you an example. This question says, arrivals of buses at a bus stop has a Poisson distribution with an average of 5 buses per hour. So we know that the number of buses that arrivals of buses, follows a Poisson distribution with an average of 5 buses per hour. So what does this mean? It means that our lambda is equal to 5 buses per hour. Now, what is the probability function if we need to calculate? If the question says, what is the probability that during 1 hour we have exactly 3 buses arriving? What is the probability function that we use? Because we have a Poisson distribution, we use the Poisson function, which is lambda to the power of x, e to the power of minus lambda, over x factorial, which gives you the probability that x buses arrive, exactly x buses arrive during 1 hour. So if the question is, find the probability that 3 buses arrive during 1 hour, we just substitute lambda to the power of 3, e to the power of minus lambda over 3 factorial. One comment before we go on. When does the Poisson distribution occur? So if we have buses arriving during an hour at the bus stop, when are these arrivals Poisson? So in other words, when does this function really apply in real life? This function, or the Poisson distribution, applies under some circumstances, under some conditions. First of all, this average lambda needs to be fixed for any time interval. So if we say we have on average 5 buses per hour, this average is fixed in any time interval. So in every hour we have on average 5 buses that arrive, so this lambda is fixed. Second, the arrivals of our event in the interval, like the arrivals of buses in the 1 hour interval, is independent. So if we have a bus arriving now, this does not affect arrivals of future buses. So the arrivals of buses are independent. As a matter of fact, that Poisson formula is actually the same as the binomial formula, in the limit when n goes to infinity, the number of times we repeat the experiment in binomial, n goes to infinity, and at the same time the probability p of success goes to 0. So if you take the binomial formula and you calculate the limit that n goes to infinity and p goes to 0 at the same time, you will get this formula in which our new parameter lambda is equal to n times p. I can basically elaborate more on this on the live session, but as a bottom line, if we have a Poisson distribution, it needs to be given all the time. So unlike binomial and geometric, in which we have to find out which distribution we have from the setting, from the context, if we have a Poisson question, it's always given like what you see here. So we say x is a Poisson random variable with parameter lambda if the probability mass function for x is given by this expression f of x e to the power of minus lambda times lambda to the power of x divided by x factorial, and x, since x denotes the number of occurrences of this event, it could possibly be 0, 1, 2, possibly going to infinity. Now, a quick comment before we look at an example that really clarifies this all. That lambda sometimes needs to be scaled. So if we say arrivals of buses at a bus stop has a Poisson distribution with an average of 5 buses per hour. What if my question is about 2 hours? What is the probability that a number of buses arrive in 2 hours? Which lambda should we use? Is it the same as 5 buses per hour, or should we scale it to 2 hours? We should scale it to 2 hours. An average of 5 buses per hour is equivalent to an average of 10 buses per 2 hours, or 15 buses per 3 hours, or 2.5 buses per half an hour, and so on, or 5/60 buses per minute. So that lambda needs to be scaled depending on the interval that appears in the question. In another setup, imagine that we have a wire, that we have a length of wire. If we know that on average, the number of flaws, mistakes in the wire, problems in the wire, the average number of flaws per millimeter of the wire, if this is 3.4, then obviously the average number of flaws in 10 millimeters of the wire is 34. So 3.4 times 10, 34. And the average number of flaws in 100 millimeters of the wire is 340. So the original 3.4 times 100 and so on. So this could be lambda, this could be lambda, or this could be lambda. The question is which lambda should we use in the question depending on the actual interval. So if the question talks about 1 millimeter, then lambda is 3.4. If the question talks about 10 millimeters, then lambda is 34. If in the question we are dealing with 100 millimeters, the question is about 100 millimeters, then lambda is 340. And let's look straight ahead. Let's look at this example, which will clarify things further. So the problem says contamination is a problem in the manufacture of optical storage disks. Do you know the CDs, optical storage disks? Sometimes the material from which this disk is made of has some contamination particles, If we have some contamination particles, then the optical storage disk, the CD, might face some problems. So what does this question say? It says the number of particles of contamination that occur in an optical disc has a Poisson distribution. So whether we have 2 particles of contamination in the disk of study, or 3 or 10, so that number of particles of contamination in the disk has a Poisson distribution. So as you notice here, we are dealing with particles of contamination that occur in an interval which is really an interval in space. We're talking about the disk, so we're not talking about buses that arrive in an interval of time, but we are talking about the disk, and we have particles of contamination that appear. But whether we have only 1 particle, or 2, or 3, or 50, this number follows a Poisson distribution, and this is given in the question. What else is given in the question? We say the following: the average number of particles per centimeter squared of the surface is 0.1. So what can we say here? This is our lambda. This is our lambda. But what is the unit of this lambda? Lambda is equal to 0.1 particles per centimeter squared of the CD or optical storage disk of study. So if our question is about the centimeter squared, then we use this lambda right away. But if the question is about another interval, we have to scale this lambda to obtain an equivalent lambda, which is simply scaled. So what else is given? The area of the disk under study is 100 squared centimeters. So the total area of our CD is 100 centimeters squared. Now let's look at the question. Find the probability that we have 12 particles of contamination in the disk under study. Was the question, find the probability that we have 12 particles of contamination per centimeter squared? No, the question is, what is the probability that we have 12 particles of contamination in the disk itself? So mathematically, we're asking what is the probability that x equal to 12, because x is a Poisson random variable. X is a Poisson, and this is given to us. X is a Poisson random variable. Okay? By the way, when we have a Poisson random variable, it needs to be stated that we have a Poisson random variable. Okay, it needs to be stated, unlike binomial and geometric, which are evident from the context of the problem or the context of the question. However, for a Poisson question, we have to say that we have a Poisson distribution. As you see here, it is given. Now, going back to the question, find the probability that x equals to 12. We have a Poisson variable, right? So what is the formula that needs to be used? X is 12. So we have lambda to the power of 12, e to the power of minus lambda, divided by 12 factorial. However, the remaining question is which lambda should we use? Should we use the 0.1, which is given itself? This would have been the case. This would have been the case if the question was, what is the probability that we have 12 particles of contamination in 1 centimeter squared of the disk? In that case, we just use lambda equal to 0.1, and the units are particles per 1 squared centimeters. But the question is, what is the probability that we have 12 particles of contamination in the whole disk? That's why our lambda needs to be scaled, and instead of using 0.1, it becomes 0.1 times 100, because the area of study, the area of the disk is 100, so 0.1 times 100, which is 10 particles per disk. So in this question, we're using lambda equals to 10. So lambda to the power of 12, e to the power of minus lambda over 12 factorial, which is the Poisson equation, lambda to the power of x, e to the power of minus lambda over x factorial, with x equal to 12. But the only remaining issue is what lambda should we use, and lambda is equal to 10. That 0.1 scaled multiplied by 100, which happens to be 10, and this gives us this formula, which is 10 to the power of 12 e to the power of minus 10 over 12 factorial, which is 0.095. A follow-up question, what is the probability that there are 0 particles of contamination in the whole disk of study? Simply, we have a Poisson distribution, a Poisson variable x, and we're asking what is the probability that x equals to 0, which is obviously lambda to the power of 0, e to the power of minus lambda over 0 factorial. I'm using the same formula, but substituting with x equal to 0. This is what you see in the red statement here, lambda to the power of 0, e to the power of minus lambda over 0 factorial. However, the second important issue is, what is the value of lambda? Can we use lambda is equal to 0.1? The answer is no. We have to use the scaled version of lambda, which is 0.1 times 100, which is 10 particles per disk, because the question is, what is the probability that we have 0 particles in the whole disk? Not the probability that we have 0 particles in 1 centimeter squared, no, in the whole disk. So that's why we have to use lambda equals to 10. By the way, lambda to the power of 0 is 1. Also, 0 factorial is 1. So the only thing remaining in this equation is e to the power of minus lambda. That's why you see e to the power of minus 10 here, which happens to have this value. As the last follow-up question, what is the probability that we get 12 or fewer particles, at most 12 or less particles of contamination in the whole area of the disk? So mathematically, it's the probability that x is less than or equal to 12. Obviously, P0 plus P1 plus P2 and so on until plus P12. And each one of these terms needs to be calculated using the Poisson formula. We substitute and then we add up the terms. If you will, this can be expressed as a summation from 0 until 12 e to the power of minus 10, because lambda is 10, 10 to the power of x or I, so this is our variable, no problem, 10 to the power of I over I factorial. So it's really easy to calculate. One last thing that we need to study for the Poisson distribution, one last fact that we need to study for the Poisson distribution is if x is a Poisson variable, what's the expected of x and what's the variance of x? It's really easy in case of Poisson. The expected of x happens to be lambda itself, and the variance of x is also lambda. Let me show you this proof here. Why is the expected value of x equal to lambda? It's supposed to be intuitive, by the way. Let me jump here over the proof. So before dealing with the proof, let me tell you what was the meaning of the Poisson distribution. We say the Poisson distribution models the number of occurrences of an event, where lambda is the average number of occurrences of the event. So lambda was by definition the average, right? So if I want the expected value of x, it's not a surprise that it turns out to be lambda. However, let's assume that we're not noticing this. Let's do it pure mathematically. So I would like to calculate the mean, the expected value of a Poisson distribution. So x follows a Poisson distribution, which means that f of x, the probability mass function, is given by lambda to the power of x, e to the power of minus lambda over x factorial, where x is 0, 1, or 2, and so on, going until infinity. From the first principles, if I want to calculate the expected value of x or mu, it is the summation of x value times its probability. So x times probability plus x times probability and so on over all values of x. So summation from x equal to 0 until infinity of x times f of x. What is f of x for a Poisson distribution? It is given by this formula, lambda to the power of x, e to the power of minus lambda over x factorial. So when we substitute, it becomes a summation from 0 to infinity x times the Poisson expression. Now let me do a simple trick which is really useful in this proof. I will talk about this proof briefly. I will not skip it. I will actually talk about it this time. X starting from 0. Let's substitute with the 0. Here we have x itself. When we substitute with x equal to 0, this is 0 multiplied by this expression, which is 0, which means that the first term in this summation is 0. In other words, this summation equals to 0 plus the term with x equal to 1 plus the term with x equal to 2. Since the first term is 0, so that summation starting from x equal to 0 is the same as the summation starting from x equal to 1. Simply speaking, because the first term has a 0 value anyway. This will be useful in the rest of the proof, so let's keep that in mind, right? What else can we do with this expression? Here we have x, and in the denominator we have x factorial. What is x factorial? X times x minus 1 times x minus 2. So basically x times x minus 1 factorial is x factorial. So that x will cancel with the x in the numerator, and then what we're left with is only x minus 1 factorial in the denominator. So the numerator has no x anymore. What can we do? So the natural thinking is to try to get rid of this x minus 1 factorial by using a substitution. Let's call x minus 1 y. Let's put x minus 1 equal to y. If x minus 1 is equal to y, this is equivalent to x is equal to y plus 1. So that y, that 1 can go to the other side. So x minus 1 is y, or x is equal to y plus 1. So what we want to do is to take this expression. What we want to do is to take this expression and convert all x into y, right? Let's start with the x minus 1 factorial. That's easy. X minus 1 is y. So what we have here is y factorial. E to the power of minus lambda is as it is. It has no x, so it stays e to the power of minus lambda. Finally, lambda to the power of x is the same as lambda to the power of y plus 1. The only remaining issue is the limits. When x is equal to 1 here, when x is equal to 1, 1 minus 1 is 0. So x equal to 1 is the same as y equal to 0. So that summation for y starts from 0. When x is equal to infinity, infinity minus 1 is still infinity, so y will go until infinity. So that summation x from 1 to infinity is the same as the summation y from 0 to infinity, and we talked about these terms. Now, what is constant and can go outside the summation? E to the power of minus lambda is constant, it has no y. It can go out of the summation. Lambda to the power of y plus 1, lambda to the power of y plus 1 is the same as lambda times lambda to the power of y, because when we multiply, we add the exponents. So lambda times lambda to the power of y is the same as lambda to the power of y plus 1. So that lambda is constant. It comes out, and then inside I have only lambda to the power of y over lambda over y factorial. Sorry, so e to the power of minus lambda times lambda is constant outside. Let's work out this summation. How does this summation look like? Let's substitute to see what it really looks like. Let's put y equal to 0. So lambda to the power of 0 over 0 factorial is 1. Let's put y equal to 1. So lambda to the power of 1 over 1 factorial is just lambda. And then with y equal to 2, it would be lambda squared over 2 factorial. The next term is lambda cube over 3 factorial, and so on. Lambda to the power 4 over 4 factorial. This is this summation. Now, does this look familiar? This is basically the Taylor series expansion for e to the power of minus lambda. We know from our previous knowledge that e to the power of lambda is equivalent to this summation or this expansion. So the whole summation here is equivalent to e to the power of minus lambda. So the whole expression becomes e to the power of minus lambda as it is, times lambda as it is, times e to the power of lambda. The first and the last terms are equal to 1, so only lambda is the remaining. We are only left with lambda, so we have just shown you that the expected value of x is equal to lambda. So if I go back to this question here, the disk, the optical storage disk, or the CD, which has basically particles of contamination. In this example, if we have the last follow-up question that says, what is the average number of particles of contamination in the disk, which is lambda itself, because expected value of x is lambda, but which lambda do we need to choose? 0.1 times 100, because the question was, what is the average number of particles of contamination in the disk? So 0.1 times 100, which is 10 particles per disk. In other words, the expected value of x, where x is a Poisson variable, is lambda. And without proof, I'm telling you that sigma square, or the variance of x, is also equal to lambda. We can also show it using something similar to this, but it's more involved, and that's why we leave it out. And this finishes our chapter. Thank you very much, and we see you in the next video, inshallah. Assalamu alaikum wa rahmatullah.